Okay guys, it's a new topics for this particular course. Food components, and one of the most important food component is water. So we cover the basics part of water, chemical and functional properties, because whatever food that you deal with is going to be water there. It's going to affect the behavior of the food during formulation, during processing, during storage, during consumption. So we have to do this, the basic properties. And food components like carbohydrates, like proteins, they have various functional groups. These are the ones that will interact with water. And like any other textbooks, basics properties or functional properties of water include as diluent and as carrier of hydrophilic ingredients. Hydro means water, philic means love, so these ingredients are water loving, yeah. And then it's also as medium for chemical and enzymatic reactions, very straightforward. Medium for dispersing and solvent actions, very straightforward. And various components of gels and emulsions, gels like tofu, like yogurt, all of these have water as a components. Of course, water is a medium heat transfer and also become plasticizer. Alright, so next we're going to consider why when we describe water structure, we would like to imagine it is a linear like this or like that, but the fact is it is not linear. It is always in this particular geometry. Yeah, there is some kind of angle there. So just want to cover a little bit why it is always in this particular geometry. You see, because of the oxygen has 8 protons and hydrogen only have single proton, the attractions of electron towards oxygen is much stronger compared to the hydrogen nucleus. So because of that, the electron tend to concentrate away from hydrogen more towards the oxygen nucleus. So the sharing of electrons in the intramolecular covalent bond is not equal. It's always going to be towards oxygen there. So this is the reason why we call water as a dipole. That means the molecule exists as asymmetrical in terms of electrically asymmetrical. I mean, it is not symmetry. Yeah, the oxygen atom bears partial negative charge there, and the hydrogen atom bears partial positive charge. And because of that imbalance in the electron concentration, it creates this angle of 104.5 degree. Yeah, 104, not 105, but it's okay, small matter. So the hydrogen bonds form between water molecules to another water molecule will result in innumerable clusters of water. Innumerable means a lot, uncountable, too much to count, too many to count. So when you drink water, you are actually drinking this water clusters, yeah, when it is in liquid state. We know hydrogen bond is weak, but there are so many of hydrogen bond, a lot of them. They results in the close proximity of the water molecules. So they exist in that form because of hydrogen bonds. Okay, unless of course you apply heat or energy, you can cause some kind of disruption to this bond. Okay, another very basic concepts what we're going to learn in slightly more detail is that the concepts of solubility. Yeah, food molecules can form hydrogen bonds with water, like salt can form hydrogen bond, some kind of ionic interaction with water. Therefore they can be dissolved or dispersed. Yeah. Okay, again we come to this terminology, hydrophilic compounds. These are compounds that hydrogen bond easily to water to form solutions or dispersions. Most of these definitely are charged. That's why it is philics, hydrophilics, or polar molecule themselves. Easy, the easy one is salts, biomolecule like minerals, vitamins, sugars, complex carbohydrates, amino acids, proteins. So how do water dissolve the substances? By hydrating them. So you must know the meaning of hydrations. It is a process by which water molecules A surround, B interact with solutes. In this case could be salt, could be sugar. Water in this case act as a solvent. Yeah, I'll show you later. Therefore, you can say water acts as a carrier for the substance that love water, like hydrophilic substances, and also as diluents of food ingredients. Yeah. Okay, this is what we call hydrations. I'm trying to explain the hydration of sodium chloride ions. Firstly, what water do, they surround the sodium chloride there. It's like a gang, yeah, trying to find a fight with the sodium chloride. Then there is interactions. Oh, sorry about the AA, it's going to be AB. B is interact. So now maybe you can see that the ions interact with water molecules and go into solution as solutes. The negative end of the water molecule, which is basically the oxygen side, attract to the sodium ions, whilst the positive end, which is this part here, hydrogen and hydrogen, attracts to the positive, attract to the chlorides ions. So because of that attraction of water molecules to the sodium ions and the chloride ions, you results in hydration of sodium ion and hydration of chloride ions. So now you can say that salt is hydrated. The electrostatic attraction of the sodium ions and chloride ions for one another, the water already control them. They are now having the attraction to sodium and chloride are now weakened. This reduces their tendency to stay in the original sodium chloride structure. So it is hydrated. You can multiply this effect by thousands, by a million. You results in the solutions of sodium chloride. So in the same way, there are other food compounds like proteins or sugars. Because of this charge functional groups existing in these compounds, you can result in the solubility in the same way like the sodium chloride being hydrated. Alright, this is definitely well known. A frog, is he an amphibian or a reptile? The clue is down there. A frog can live in land and also in water, so it is definitely an amphibians. Why? Okay, amphiphilics. This is just a term that's similar to the amphibians now. These molecules like proteins, certain vitamins, phospolipids, sterols. These are very special molecules because they contain both hydrophilics and hydrophobic regions in their structures. As food technologists, you're going to come across a lot of these amphiphilic molecules, and because of their unique structures, unique properties, they're going to create many interaction with many other food compounds, not just water. Okay, but in water, what amphiphilic molecules can do, they can form micelles. What is micelle? It is clusters of molecules in which the hydrophobic groups are directed away from the water. Remember, hydrophilic is water loving, now hydrophobic is water fearing, water phobia. While the polar or the philics, the charge groups, are exposed on the external surface. I will show you. And the non-polar hydrophobic groups form stable inner core due to hydrophobic interactions. So quite a number of amphiphilic molecule exists in nature, in food products as the clusters or as micelles. You will learn in food chemistry some of these micelles. Yeah, so micelles are actually stabilized structures of amphiphilic molecules. There, water molecules there with oxygen and hydrogen, partial negative and partial positive, and then we have these amphiphilic molecules. Just to remind you that this is philics, meaning water loving, and then hydrophobic. And so, like we described earlier, that the head as a hydrophilic end will tend to be attracted to the water molecules, while the hydrophobic end is somewhat afraid of the water molecules. They stay away. Because of this behavior, you form a micelle in such order manner to surround, making the water able to surround amphiphilic molecules. So as a result of this, you have micelle stabilized. Yeah. So this is a very basic concept about water. We talk about solubility, hydrations, and how not just things like sodium chloride, straightforward hydration, but you can also hydrate things like amphiphilic molecules, having both hydrophilics and hydrophobic regions, forming also the clusters of molecules. Yeah. Okay guys, so we'll meet again. We'll talk about in detail more about water as food components, but this time we'll talk about the water activity and its consequences. Okay, so happy learning.